It's positive for this shit that you have. So it's the same.
Okay, so if we want to find the domain for a rational function, what do we need to do? Set the denominator equal to 0. Okay. So for example, in number 3, I take x minus 3, I set it equal to 0, I get 3. What does that tell us? That there's a problem at 3, right? It doesn't give us the domain exactly. It gives us, the math word is complement, but it gives us the opposite of the domain, right? It tells me that 3 is an issue, right? Because at 3, this would become 1 over 3 minus 3, which is 1 over 0, and dividing by 0 is not defined, right? And the domain is finding where a function is defined. So 3 is a problem. That means the domain is everything else. So setting the denominator equal to 0, finding those zeros gives us the, in some sense, opposite of the domain. So for number 3, what is the domain? It's everything that's not x equals 3, right?
So it'd be negative infinity, 3 union 3 to infinity.
Yep. Everybody okay with that? Yeah, these are all already factored, so we should pretty much be able to just kind of look at them and spot what's going on. If they weren't, like you'll see in homework at other places, I would maybe start by factoring or using the quadratic formula or whatever, but finding the zeros of the denominator. Okay, so what about 4? There's going to be problems or trouble when x is 1 and negative 2. So the domain is everything apart from negative 2 and 1. Those don't work. Domain is everything else, which means we're going to have to write it in 3 separate intervals that we union together. What would that look like? Yeah, nice. Yeah, good. Okay, cool. And 5 and 6 real quick. Everything except for negative 4. And then the last one, negative 3 and 4. Same order that show up on a number line. So just, be careful about writing out the intervals, negative 3, then negative 3 to 4, then 4 to infinity. Okay. Now, those points that we're finding, right, the zeros of the denominator, for example, in this one, negative 4, those are sometimes called discontinuities. Those are places where the function fails to be continuous, meaning that, if I'm drawing it, I have to lift my pencil up or whatever. Those are where the function sort of separates into separate pieces. The other thing we need to be able to do is, one, find them. That's what we've just done. But then we also need to figure out what happens there, right? Sometimes that's called classifying them or describing what the function does there. So let's look at, I don't know, let's look at 4 maybe. Just want to pull up a graph of one of these. Is it x minus 1 and x plus 2? Is that right? I'll just look it up. 1 and -2 were the places that we decided, we need to kind of focus in on and look at, right? The graphs of these, again, are a little bit like different than the stuff we've seen up to this point. If you graph these in a graphing calculator, they look super bizarre, right? Sometimes because of the, tiny, chunky, pixely screen, right? So just kind of be aware of how we read that. Sometimes in a calculator, it might even like draw in stuff like that. That's because you're close to 0 and computers have a problem with that idea. So just kind of be aware of all that. But what we need to look for is what happens at -2 and what happens at 1. If I look at x equals -2, right? 0, -1, -2 right here. What do we see? Yes. And that line's called an asymptote, right? It's a vertical one, but right here, there's a vertical line that graph is sort of breaking around, right? That it's sort of, fitting into that gap is this vertical line at x equals -2. The same thing happens at 1. So this has 2 vertical asymptotes. They are, which one was that? 4? X equals -2 and x equals 1. Okay. Now the reason those vertical asymptotes show up, let's take a look at that same one, but let's think about what happens if I tried to plug x equals -2 into it. 1 over -2 minus 1 times -2 plus 2. So that's 1 over, this is -3, but -2 plus 2 is 0. So 1 over 0, right? Now again, 1 over 0 is undefined. And that's why the function's not continuous there. That's why we leave it out of the domain. This x value, that's why we get a vertical asymptote there. The thing that makes it a vertical asymptote is what happens nearby. So right next to -2, right? Right next to where the trouble is, where the discontinuity is. If I plug in a value like -1.99, what I'm going to get is 1, because that's all that's in the numerator, divided by something that's almost 0, like a really small decimal number, right? If you take something like 1 and divide it by a really small number, what kind of thing do you get back? A really big number, right? The closer you get to this, the bigger that value is going to get when you take its reciprocal or when you divide by it, right? That's why, back to my graph, at x equals -2, we see this do what it does. If the x values are really close to -2, then what happens is that I get back bigger and bigger values when I do that division or when I take that reciprocal. That's why the thing gets really steep, sort of suddenly like near that line, and why it starts to kind of like hug in toward that line the closer and closer you get. Right now we're looking at like a really narrow but tall strip, like around where that asymptote is. And you can see like the further out I go, the more this curve just kind of approaches that line without ever quite getting there. This is why, right? 1 over 0 is undefined, but nearby it's like 1 divided by a really tiny number, which is a really big number. That's why it does what it does. Okay. The same thing happens for all the rest of these. So this has a vertical asymptote at x equals 3. This has a vertical asymptote at x equals -4. This has 2 of them at x equals -3 and x equals 4. They are lines, right? They're equations of vertical lines. That's why I'm writing the x equals every time. Watch out for that. But let's compare this to something like this. So this is a new problem I just wrote down. Denominator looks a lot like the number 4, whatever it is, but I changed the numerator, right?
Divide the numerator into the denominator.
Kind of. Yes,
You'd be left with 1 over x minus 1.
right. Kind of. Just so yes, but put an asterisk by it, right? And we'll look at what's going to happen. So if I'm interested in finding the domain, I do the same thing, right? That doesn't change what happens with the domain. I still look at places where the denominator is 0, which would mean that the domain is still everything except -2 and 1. And yes, we look at this and we see the x plus 2 in the top and bottom, and we are very tempted to cancel or reduce those out, right? Because you see the same thing show up in the top and bottom. Like I want to simplify that, and you almost can. You can everywhere except one point, and I'll show you what I mean. If I look at this though, put that other asymptote in there too. So -2 and 1, right? What do you see at x equals 1? An asymptote, right? There's a vertical asymptote. There's a clear break in the 2 sort of pieces of the graph, and there's this line I can imagine sort of fitting in there, and that's all good, right? What about -2 though? Is there an asymptote at -2? Definitely not, right? This line that I put in there, that makes sense, right? The graph, kind of follows that. This one, that doesn't, right? That looks totally out of place. What happens at -2 with this one that didn't happen with the other one is exactly what Taylor pointed out a second ago, that this x plus 2 factor, I really, really want to cancel that. So what happens if I try to plug x plus 2 into that, or -2 into that? That's different is that I get 0 over 0. Dividing by 0 is still undefined. But this thing, 0 over 0, this is what's called an indeterminate form. You don't really need to know that, but all that means is that I need to look a little more closely at what this thing does. This is not as bad as what happened before, right? The other one, we had something like 1 divided by 0. You divide 1 by a really tiny number, you get back a really big number. And the closer you get, the bigger it gets, and that's why the thing grows the way it does. Here, that's not happening. If we're nearby this point where it's discontinuous, what I get is basically the same thing on the top and bottom. So those are going to kind of balance each other out, right? And sort of cancel, and sort of not cause that same thing to happen. But look at this. At -2, if I could get my finger to hold still long enough, at dang it. Really takes nerves of steel. At -2, the function's still undefined though. It's still not in the domain. But what happens is instead of this sort of infinite discontinuity where it breaks and you get the asymptote and everything, there's just a single missing point. It's like you just erase that one point and go around it. The open circle means the same thing it always does. That point's left out. We call that either a hole or a removable discontinuity, if you want to sound fancy. But that's what happens there instead. And it's because of this. So this thing has a vertical asymptote at x equals 1, but it has a hole when x is -2 because of, again, this factor that shows up in the top and the bottom. For the most part, we're not going to see all that much stuff where a hole or a removable discontinuity actually shows up, but that's how you kind of look for them or deal with them. It's when it's a thing that gives you zero on the top and the bottom, or you have a common factor in the top and bottom that you would like to cancel like that. And the only difference, and I said like you can cancel it, but put an asterisk by it. The only difference is that this thing does look just like 1 over x minus 1, except for an x equals -2. The only difference is that this would give you the exact same thing, but without that hole. Like it'd be filled in all the way.
Okay.
Yeah, that's the only difference. So you just need to be aware that, there is that one little point where it's going to do something differently.
That is-
Okay. So that's all of that's dealing with X values basically, right? The domain, figuring out where it's undefined, figuring out what happens at those discontinuities. The other thing that we need to look at and spend some time talking about is how to deal with in behavior. In behavior, meaning not the middle of the graph, but what happens eventually once it kind of settles down, right? And settles in for what it's going to do for the rest of forever. So this is what happens for very large, either positive or negative X values. How do we figure out in behavior for polynomial stuff? Yeah, the degree and the leading term. Right, degree told you whether the ends go the same way or opposite directions, and then the leading coefficient told us about up or down, basically. Right, we're going to do pretty much the same thing here, and look at the leading terms. Because now there's a polynomial on top and there's a polynomial on bottom. We're going to compare the two. So take 5 maybe, for example. I'm just going to work here. What are the leading terms in the top and the bottom of that function number 5? X over X. Okay. Just like with polynomial stuff, the farther out I go, the less that the trailing terms matter, right? Because the less that they contribute. If X is 100 million, I don't really care that much about the difference between 100 million versus 100 million and 4, right? So the trailing terms don't contribute as much. The leading terms start to like dominate more and more. So we take those leading terms aside. X over X. Taking those aside helps me see kind of bigger picture what the thing is going to do, because I can do algebra there that I can't do with the whole thing. If I had just X divided by X, what would you like to do with that?
Cancel that.
Cancel, right? I mean, the thing that like we always want to do, even when it's not appropriate to cancel, is cancel and reduce stuff, right? To simplify it down. What would X over X cancel or reduce to? 1. Well, let's take a look at it. Y, that's not a Y. Y equals X over X plus 4. Okay, here it is. Here it is a little bit zoomed out. Just in words and directions and pointing, whatever, first of all, how would you describe the end behavior of this thing? Not the middle, but the ends. Which way do we need to point to describe what the ends are doing? Like that, right?
Yeah.
I mean, polynomial stuff, it was always up or down, or right? Now, I mean, these are pretty much level, flat, right? That end goes that way, that end goes that way. So it's leveling off. That means there's a horizontal asymptote, right? I can imagine a horizontal line that kind of fits in there that shows what the ends do, right? if there's a horizontal asymptote, we need to figure out where it is. Where does it look like it is?
Horizontal asymptote is one,
Looks like it's at 1.
and then the vertical.
Let's graph y equals 1 just to, kind of have a better like little guide there. Everybody buy that appears to be the horizontal asymptote? Okay, where else have we seen 1 show up with this function?
When we divide x by x.
Right there. I need a longer pointing thing. Right there, right? Okay, so what this thing does, what we're doing basically is simplifying stuff down enough that I can see and analyze what's going to happen when x is 100 bajillion without all of the noise getting in the way. What this is a polynomial on top and a polynomial on bottom that are about the same size. So what's going to happen then is that they're going to kind of balance each other out, which makes the whole thing level off. And where it levels off is 1, because these were both just x, and that reduces to 1. Oh, I'll actually write it this time. This has a horizontal asymptote, which I'm going to start abbreviating because it's too much to write, at y equals 1. Everybody see how that works? How would things change if this had been 2x over x plus 4? It's not number 5 anymore. This would have been 2x. And so reducing would have given us 2. And so the horizontal asymptote would be y equals 2. What if this had been 2x over 3x plus 4?
Be 2 over 3.
It'd be 2 over 3. They're still basically the same size, meaning degree, right? They're the same kind of thing. They're both linear in the top and bottom. So they're going to balance each other out. And where that's going to happen is that, well, they're basically the same size, except in the ratio of 2 to 3, because this one gets doubled, but this one gets tripled, so it's a little bigger, right? So they're going to balance out, but at 2/3, right? That's where it's going to level off. That is something like you're not really going to be able to just look at it and see that 2/3 is where the horizontal asymptote is, right? With like to that accuracy, you can tell that there is one, right? You can see it kind of leveling off, but to actually figure out what it is, that's when we kind of get into the leading term thing. Is that okay? Everybody feel all right about that? I always, kind of think of this as being, sort of balanced, right? If you want, you can picture the sort of like old timey like scale thing, right? They're about the same size, so that's going to cause it to level off. And then you look at the leading terms to figure out where. Okay, what about, let's do the same thing with number 4. I need the leading terms. It's factored. I'm not going to actually multiply the whole thing out, but I am going to do enough to see what the leading term would be. So in the denominator, x times x would be x squared, and then everything else is going to be smaller than that, right? Okay. So the leading terms, 1 over x squared. Can we do anything to simplify that? Like we did the last one? No, right? It's just, it is what it is. It's already in lowest terms. I can't reduce or cancel anything. It's just 1 over x squared. What we need to do then is think about what that's going to do when x is a billion, right? When x is some big number, what is this going to do? If x is really big, then x squared is bigger, right? Like it's more. 1 divided by something really big. is really small, right? 1 divided by, you're taking the reciprocal. The reciprocal are really big numbers, a really small number. So what's that going to do when x is big? Is that that's going to be closer and closer to 0, right? It's going to be positive because x squared is positive, positive divided by positive. But the farther and farther out I go, the more and more that thing is going to just kind of get squashed down onto the x-axis, right? So it's going to level off, but at 0. And you can see that from the graph as well. That means that this has a horizontal asymptote at y equals 0. This same kind of thing would happen for anything that is kind of bottom heavy like this. Again, that's sort of how I think about it. The degree in the bottom is bigger than the degree in the top. Anything where that happens, the same kind of thing is going to happen, right? So if I had taken the leading terms and it was x over x to the 5th, if I reduce that down a little bit and cancel that 1 over x to the 4th, right? That's bottom heavy. The denominator is growing, the top is not. That means the whole thing is going to get just smushed down onto the x-axis kind of over time, more and more. So that would again give us a horizontal asymptote at 0. Okay. So let's look back at, so we did 4 and 5, right? Tell me about 3. Leading terms 1 over x. When x is big, 1 over x is small. So this would have a horizontal asymptote. At y equals 0. Again, because that leading term is going to go to 0 as x goes to infinity. Is that when x is big? What about 6? What are the leading terms there? X squared over x squared. Again, we don't have to expand the whole thing. We just need to know what the leading terms look like. X squared over x squared would reduce to 1, or yeah, x over x first and then 1 over 1, right? Because you can reduce further. So 1 total. So the horizontal asymptote would be y equals 1, right? Those are kind of balanced. They're the same size. That's going to level off somewhere here, 1 over 1. And if there had been a leading coefficient here or something, then it'd be that ratio. Okay. So there are kind of 3 different ways that can go, right? Either they're sort of balanced to each other and have the same degree, which means it's going to kind of flatten out somewhere, right? Whatever that ratio is. Or like this one, it's sort of bottom heavy. The other option would be that it could be like top heavy, right? If I'm interested in the end behavior, we can find other stuff too, but if I'm interested in the end behavior, I just want to look at the leading terms. So x squared over x, which we can simplify, right? To what? X over 1 or just x, right? What's that going to do if I let x grow without bound? If I let x go to infinity? What is that going to do? If x is big, then x is big, then x is big, right? Because it's the same thing. Let's take a look at the graph of this thing and see what it does. I don't even remember what I said, but it doesn't really matter. how would you describe the end behavior here? That end's pointing up. That end's pointing down. Does it have a horizontal asymptote? No. There is what's called an oblique or a slant asymptote in here, like a diagonal line. Does everybody see that this diagonal, or somewhere in here, this diagonal line kind of shows what the ends do? That's called an oblique asymptote or a slant asymptote. We're not actually going to find those. The way you would find it is to just do the division. And then what you get is a quotient is the oblique asymptote. We're not going to actually get into finding them, but that's what that's called. I would describe the end behavior as, like I would do with a polynomial, as, being something like that. But this doesn't have a, so the ends went like this. This doesn't have a horizontal asymptote. Now, don't hear me saying like, just memorize these 3 cases or whatever, but that's kind of how it breaks down, right? Either they're the same and they balance each other out, or one has higher degree, which forces the thing to either, sort of grow, and it could be going, up or down, but, not leveling out, or if the bottom is bigger, then it kind of forces the whole thing down to 0. Okay, questions about stuff? All right, similar to if you haven't gotten into the homework for this week yet, which surely you have, but it's kind of similar to the polynomial graphing stuff in that a lot of the questions in there are kind of broken up into smaller pieces, right? Like it's going to give you a function and ask you to find the domain, or ask you to find if there's a horizontal asymptote, or ask you to do like one thing at a time. There's not a lot of them that are going to be sort of putting it all together, but that's what we want to be working on, just like we did with the polynomial stuff. So if I give you a rational function, these are things that you ought to be able to do. Find the domain, find the vertical asymptotes, or find any holes if there are any, but basically classify those discontinuities. Find the horizontal asymptote if there is one, or describe the end behavior and say like, it goes like that or like that if there's not. Again, we're not going to need to actually be able to find a slant or an oblique asymptote, but just be like aware that that's what it's called. Because you'll see some stuff in the homework where there's like multiple choice, it'll say like, there's an oblique asymptote, here it is. And conveniently, none of those problems will you ever need to actually use that answer option, but it's there. And then find the X and Y intercepts. You find these the same way you always do. X-intercepts are where Y is 0, Y-intercept is where X is 0. So what I want us to do with the time we have left is spend some time just working through this example that I just made up. Find the domain, find the asymptotes, find the horizontal asymptotes, find the X and Y intercepts. That's basically everything that we're, ever really gonna learn or know how to do for one of these as far as this class goes. So that's kind of everything all at once. So